Homework 9, Section 5.2, the addition rule complements Video 2. Let's take a look at what's called a contingency table. I meant to underline the word table also. A contingency table is just a table that organizes information usually from two perspectives. For example, 1,000 adults were surveyed and they were asked two questions. Question number 1, are you likely to vote or are you not likely to vote? And question number 2, for a certain proposition, not sure what the proposition or law was, they were asked whether they favor it, whether they're opposed to it, excuse me, or whether they're undecided about the proposition. Of the 1,000 adults, 372 of the likely voters favored the bill, 262 of the likely voters opposed the bill, and 87 of the likely voters were undecided. And of the ones not likely to vote, 151 favored the bill, 103 opposed the bill, and 25 were undecided about it. There are a lot of probability questions I can ask you from this contingency table, but I'm going to ask you four. Number 1, what is the probability that one of these adults favors the proposition? Number 2, what is the probability that of these 1,000 adults, they are likely to vote? C, what is the probability that somebody is likely to vote or favors the proposition? And remember, that includes the possibility that they're both. And D, what's the probability that somebody is likely to vote and favors the bill? So let's take a look at them in turn. If we want to know the probability that one of these 1,000 voters favors the bill or the proposition or whatever it is, we need to know two numbers. We need to know the number who favor and compare that to the total number. So basically, what fraction of the 1,000 adults favor the bill? Well, out of the 1,000, these two numbers represent the ones that favor them. So let's just go ahead and add those up real quick. If we add 372 and 151, we get 523. So the probability that one of these 1,000 adults favors the bill is a little more than 50%. In fact, it would be easy to turn into 52.3%, but let's leave it as a fraction. What about the probability that somebody is likely to vote? Same concept. We need the total number for the denominator, but in the numerator, we need the number likely to vote. So what would we do to find the number of people who are likely to vote? Well, the first row represents everybody who's likely to vote, so we would just have to add 372, 262, and 87. 1, carry the 1, 8, 14, carry 2, 5, 6, 7. I believe it's 721, but I'm going to add them again just to make sure. 372 and 262 is 634, plus 100 is 734, but that's 13 too much. 721 is correct. So the probability that somebody is likely to vote is 721 out of 1,000. Not a bad voter turnout, 72.1%. But for the compound events, we have to think a little bit more carefully. For example, what's the probability that somebody is likely to vote or favors the bill? Well, it's going to be out of 1,000. I think we know that already. But what are we going to put on top? Where are the people in this contingency table that are likely to vote or favor the bill? Well, the ones that are likely to vote are here. And we already know that that adds up to 721. And the ones that favor the bill are here. And that adds up to 523. So should we just add the 721 plus the 523 to get the total number of people who are likely to vote or favor the bill? I don't think we should do that. Because if we add 721 and 523, that's going to be more than 1,000. It's going to be 1,244. Probabilities can't be bigger than 1. Plus, there's not that many adults. It's more adult. It's a greater number than the number of voters, which I guess in some parts of the country that can happen. But I digress. So why is adding the 721 for the likely voters and the 523 for the number who favor the proposition not the best strategy? The answer is we double counted somebody. We double counted these 372 people. These 372 people were counted once when we added to get the 721 and once when we added to get the 523. So how can we find the correct number? Well, there's a couple of ways. Number one, we can just add these four numbers. Number two, we could add the 721, we could add the 523, but then subtract 372 once because we accidentally added it twice. Let's go with the first approach where we just add the numbers that we're looking at. So 372 plus 262 plus 87, that's the top row, plus the 151. Let's see what that equals. Well, I already know what the first three numbers add up to. They add up to 721. So I just had to add the 151 to it, and it looks like it's going to be 872. So to find the OR probability, or to find the numerator for the OR probability, we couldn't just add these two numbers. It would have been nice, then we would have just added the previous two answers over there. Let's take a look at the AND. The probability that they are likely to vote and favor the bill. Kind of running into this answer, but please forgive me. So out of 1,000, how many people in this contingency table are likely to vote and favor the bill? We actually don't have to do any math, we just have to look in the right place. Which people belong to both the first row and the first column? These 372 people. So when you're calculating a compound probability, or the probability of a compound event, whether it's or and you have a contingency table, be very careful. If it says or, and you're looking for a particular row in a particular column, but be careful not to double count where they intersect. And if you're looking for the probability of a compound event using and, that's a little easier. You're just looking for the intersection of a row and a column.